wish this gave some indication that it was happening, but as far as I can tell, it's not. Anyway, we'll start with this problem, a projectile motion problem. And this is going to completely bypass the things that we did back when we were studying projectile motion and figure this out in a completely different way. So we're going to use the work kinetic energy theorem to determine the maximum height reached by a projectile. And we have an initial speed. Doesn't matter what that happens to be. I made up an angle for this. And so we can, it could have been any initial speed and any initial angle. We'll still be able to figure out the maximum height of it. So this is just sort of an example problem. And I wanted to start off by just making a little sketch here. If this is V naught, we would have, we could figure out the components of this, and the X component is V naught cosine theta. You've seen that before. Y component is V naught sine theta. And I was going to do something here. V naught cos theta squared plus V naught sine theta quantity squared is equal to what? Well, if you expand these things outward kind of, you'd get V naught squared cosine squared theta plus V naught squared sine squared theta. And that will equal V naught squared times cosine squared theta plus sine squared theta. And stop and think for a minute what that's equal to. It's actually equal to V naught squared. Well, it makes sense. In a right triangle, if you've got V naught cos theta on one side and V naught sine theta for another side, the sum of the squares of the sides will equal the square of the hypotenuse. And that's what we happen to have. But this is something that shows up in the kinetic energy. And the initial kinetic energy of this projectile is going to be 1/2 mv naught squared, which we could split into 1/2 v naught sine squared theta. It doesn't matter what order we write it in, plus 1/2 m, let's see, v naught squared sine squared theta, v naught squared cosine squared theta. Okay, and so you can divide that initial kinetic energy into two chunks, one of which represents the horizontal motion, the other represents the vertical motion. Now, of course, you can combine them back together, but that may help us solve this problem here. So let's also consider, I wanted to show you something else that comes out of this. Let's suppose that we consider some little instant of displacement, and this could be some little delta r or even a dr, and we'll look at the work that's done by the gravitational force while this thing is going sideways a little bit and up a little bit. Yesterday we saw an expression that the little bit of work that's done in something like this, or maybe we could call it delta W here, but it'll be the force dotted with the displacement vector. Okay, and as we shrink this down, we could actually think of this as going to some little vector dr, and then instead of a delta W, we could talk about a dW. But the dot product is going to equal the magnitude of this vector, mg, the magnitude of this vector, which is delta r, and the cosine of the angle between them. So let's see, I probably shouldn't use theta here because we were using it for something else earlier. Let's just call it the cosine of phi. And so right here, This whole angle is phi. Okay. Now, cosine of an angle bigger than 90, I couldn't remember what the formula was, so I had to look it up, exactly what it happens to be. But I'm going to split that angle phi into a 90-degree angle and a little bit more than that, or more than that. And so phi is going to equal 90 degrees plus beta. So I'm just going to split it up like that. And so the cosine of the sum of two angles is actually equal to, now this is a lot of trig to go through for something that's relatively simple, but that's okay. It'll be the cosine of 90 degrees, the cosine of beta minus the sine of 90 degrees, sine of beta. And this just comes out of a trig formula. I don't remember that one got derived, but it's the sum of two angles. And if you just had alpha plus beta, it'd be the cosine alpha, cosine beta minus sine alpha, sine beta. But in this particular case, that's what it is. Well, the cosine of 90 degrees is 0. So this term vanishes. So that thing's gone. Sine of 90 degrees is 1. So what it ends up being is the cosine of 90 degrees plus beta is just equal to minus the sine of beta. Okay. When you go past 90 degrees, the cosine goes negative on you. And so that's what this ends up being. Well, when I use that up here, delta R, if I draw a little vector here, or thing like this, here's that beta, here's delta R, and this upward part is the displacement in the vertical direction. That's delta R sine of beta. That's what that happens to be, but it's minus the sine of beta. So when the thing is going uphill like that, the little bit of work that's done when it displaces upwards ends up being minus mg delta R sine of beta. Okay, and I just defined beta to be that, but delta R sine beta is just delta Y. So delta W is minus mg delta Y. Okay, that's just the height that it increased by. The horizontal motion doesn't matter at all in figuring out this work. Turns out the work that's done by the gravitational force is independent of the path you're taking. You could have the thing doing loop-the-loops going all over the place, and it starts down here and ends up there. The only thing that matters for the total amount of work that's done is the difference in height between those 2 points. And if it's going upwards, the work that's done by gravity is going to be negative. So let's use that idea to solve this problem here that we started with. Work kinetic energy theorem to determine the maximum height reached by the projectile. Okay, that tells us that the change in kinetic energy is just going to equal the work done. It's going to be minus mg, and it's launched from ground level. I'm going to call the height above that at maximum y max. Okay, and so that'll be the change in kinetic energy. Well, what's it going to lose in kinetic energy? It started off with 1/2 mv naught squared. Whoops, writing this in the wrong order. 1/2 mv final squared minus 1/2 mv naught squared is going to be minus mg y max. Well, let's see. I've got m's in every term, so I can just drop those things out. And I'll have 1/2 V final squared minus 1/2 V naught squared is going to equal G times Y max with a minus sign here. Okay. Well, what's the final velocity going to be? Think about this. When you have a projectile that's launched, as it's going up, it loses its vertical velocity, but the horizontal velocity never changes. There's no force in that direction. And so V final squared is going to end up being, well, it's just going to end up being this thing, V naught squared cosine squared theta. And I'm going to split this into two parts. I'll have 1/2 V naught squared cosine squared theta minus 1/2 the V naught squared we knew was V naught squared cosine squared theta plus V naught squared sine squared theta. Okay, well, I've got a 1/2 V naught squared cosine squared theta inside and out squared, outside, I mean, and I'll end up with minus 1/2 V naught squared sine squared theta. That's the, actually, if I stuck an M on there, that would be the lost kinetic energy, or the change in kinetic energy. And that will equal minus G Y max. And, let's see, minus on both sides, I'll end up with Y max is going to equal V naught squared sine squared theta over 2G. This is actually V naught Y that I've got up here. V naught squared, or V naught Y squared, is what this ends up being. And that's divided by 2G. We'd come at this thing before. Now, I went to a lot of work to show this, but the crucial part is this. That's the work done by gravity. It's the force. And since it's going opposite the force, we've got a minus sign on that. The force times the height gained, force of gravity times the height gained, but it's opposite the direction of the force. So it's a negative work that's done in this case. And that's just going to equal this thing. And so we could have almost just started with this and worked through this last little bit of algebra here, and we would have been done. All right, now we could plug in the numbers here, but I just wanted to show you that thing, and you can see how it works. Okay, this is a problem that was on the tail end of the handout that I gave you yesterday. And it says, suppose you throw a rock straight down into a deserted quarry from the edge, which is 18 meters above the bottom. It has a speed of 21 meters per second when it reaches the bottom. What was the rock's speed when it left your hand? Okay, now we're going to use this work kinetic energy theorem to figure this thing out. Well, okay, so here's you up here standing on this thing, and you throw a rock straight down with some speed V naught. When it reaches the bottom down here, it's got a V final, and the change in kinetic energy will equal the work done on it on the way down. Well, the work done on it on the way down, in this case, mg is going to be downward. So is the displacement for this thing. And this, we don't have to worry about angles on because they're both in the same direction. The work done by gravity is going to be mg times the displacement. They're both in the same direction, so it'll be a positive amount of work. And it was 18 meters that we'll have on here. That will equal the change in kinetic energy, 1/2 mv final squared minus 1/2 mv naught squared. Okay, work equals change in kinetic energy. Now, this is positive, so it's going to be speeding up on the way down, but we want 1/2 mv naught squared. So let's just rearrange this. 1/2 mv naught squared, that's a v, is going to equal 1/2 mv final squared minus mgd. Notice there's an m in every term again, and I'm just after v naught. So if I do a little bit of algebra, multiply everything by 2, I'll get, let's see, the m's are gone. And I'll get v naught squared is going to equal 2v final squared minus, whoops, no 2 on that term, minus 2gd. So we can just plug in the numbers here. Square root of, and this was v final. Don't talk and write at the same time like I do. Anyway, v final is 21 meters per second. So 21 meters per second squared minus 2 times 9.81 meters per second squared times d, which is 18 meters. Unit-wise, this will be meters squared per second squared when we square it. This times that will give me meters squared per second squared. So everything's meters squared per second squared on the bottom. Has to be, or you can't add or subtract them. And when you take a square root, you'll get meters per second. So that one's not so bad anymore. I should know 21 squared in my head, but I don't. But it's going to be more than 400. So hey, good attendance today. We've got 7 people here. That's a record, I think. Okay, I need to take the square root of that. 9.4 meters per second. Okay, that wasn't bad. I mean, really, what we were solving was mgd equals 1/2 mv final squared minus 1/2 v naught squared. And sometimes energy stuff makes things really easy. Sometimes it makes things possible that are not at all possible without them. Then, if you throw a rock horizontally from the same initial height with the same speed you found above, with what speed will it strike the bottom of the quarry? Well, in the last problem, I showed you that the work done by gravity is path independent. All that matters is the change in height. We're going to have the same thing here, which means we're going to have the same change in kinetic energy. And these are speeds squared. They're not velocities, they're the speeds. Whoa, this is a little bit weird, but if you think about it, it's going to gain the same amount of vertical speed on the way down that it gained in the first problem. Now, it won't have the same vertical speed when it reaches the bottom that it had here, okay, but it's going to have a horizontal speed that doesn't change all the way through, and you'll end up with the same thing. And so you don't have to do any work, because the work done by gravity is going to be the same. You could just say mgd again is going to be 1/2 mv final squared minus 1/2 mv naught squared. And this thing's the same, so v final is going to have the same speed as it did before. In fact, you could throw it upward with that same speed v naught. You could throw it straight up with that same speed v naught. Do anything you want, any angle, you're going to end up with the same final speed at the bottom. And so it doesn't matter what it happens to be. And that's because the work done by gravity as the thing goes, whoops, it actually goes from here down to here, depends only on the difference in height and not the path that it took. So again, whether it's doing a path like this, or whether it's going straight down, or whether you threw it up and it does something like that, the delta y is the same in either case. And so the work done by gravity is going to be the same. We call that path independent when that happens to be the case. Okay, something that I didn't do yesterday, I started by showing you the if we had a force versus displacement graph, like F versus X. And the one we started with was one where we had a positive force, and we found out that the area under this curve ends up equaling a change in kinetic energy. And I introduced the idea of this X initial and X final, that the area under this curve we could write as this weird symbol from X initial to X final of, if we think of this as being some function of X, and in this case it's a constant, but in general, it could look like this, f of x dx. And all this gobbledygook means, which if you're in first quarter calculus you haven't seen yet, it just means the area under this graph. Okay, well, let's introduce a new type of force, and this is a dividing line here. This is going to be something called Hooke's law, and it'll be a Hooke's law force, is what we're talking about. Robert Hooke was a contemporary of Isaac Newton's. The two did not get along well. Newton was kind of a jerk at times, and he made fun of Hooke's short stature. He wasn't very tall, and among other things. But sometimes intermediaries would go between the two to talk about things, like Edmund Halley was someone who worked with both Hooke and Newton. And sometimes if Hooke and Halley were working on some problem, or yeah, Halley would go to Newton and ask him about it. And actually, that was how the public found out that Newton had figured out the law of gravitation. Newton had figured it out decades before and never told anybody about it. And then Halley went to him. But anyway, Hooke was this guy, and he studied spring motion. And he found out that if you have something like a spring, that maybe it could be on a horizontal tabletop, or it could be vertical or something like that. And over here it's attached to a wall, something like that, that the force that's exerted by the spring ends up equaling minus kx. The force is proportional to the amount of stretch or compression that you give to the spring. If you extend the spring outward this direction, the spring will pull back. I'm assuming this is the equilibrium position of the spring. And so if this is, maybe you can define x to be 0 right at the equilibrium position, then you stretch the spring by some amount x, the spring will push back in that direction with a force minus kx. If you compress the spring, so you've got some x that's in the negative direction, then the spring will push back with a force that's proportional to the amount that you compressed it by. And that's what this shows up as. Now, there are limits to this. With any spring, if you stretch it too far, you're going to cause a permanent deformation of the spring, permanently deformed, and it's not going to pull back like it did. And you can do something similar if you compress it too much as well. So it'll have some limits to it. Okay, but let's see what kind of work we get done when we have a force that behaves like this? Well, if I make a graph of this, this is going to be my f as a function of x graph versus x with something that has a slope that goes like that. Here's what that graph looks like. The slope here is going to be k. By the way, k is something called the spring constant. It's different for every spring that you might look at, and it's got units of newtons per meter. So, or sometimes newtons per centimeter, although if we actually want to get the force in newtons, we'll have to have it in newtons per meter, unless you're measuring the distance in centimeters, and then newtons per centimeter is okay. But K is going to be some number of newtons per meter. This is just the units of it, or some number of newtons per centimeter. And we'll do an experiment probably next quarter where we'll measure the spring constant of some springs that we have at school. And turns out there's some interesting things that happen when you have a force of this type. And you might think, well, whoopee, springs, not that big a deal. But it turns out that a lot of forces in nature for small changes in a distance will behave this way. And one of the forces that does that is if you have atoms that are in a molecule, so it's what's called a diatomic molecule. So this would be atom 1 and this will be atom 2, that they'll be held together by an attractive force, and they reach an equilibrium position, and the attractive force is caused by the electric charges of the two atoms, possibly rearranging themselves so that there's a balance between attraction and repulsion anyway. But when that's the case, if you try to push those atoms closer together, that force for a while will be proportional to the displacement from the equilibrium position. And the same thing happens if you try to pull those two atoms apart. And what can happen is that the two atoms, if you try to displace them, they end up bouncing back and forth together, just like a mass hanging from a spring will end up bouncing up and down. And so you can use some of the mathematics that we'll develop next quarter for a mass bouncing up and down on a spring would work for two atoms in a diatomic molecule. And so you can use some of the same mathematics for something like that. And when two atoms happen to be doing that, bouncing back and forth, they'll give off electromagnetic radiation that's energy-wise, it's proportional to the frequency of oscillation between the two things. So you can study stuff about molecules just by knowing the mathematics of stuff about like this. Anyway, let's figure out the work that's done as we go from, this would be the origin, then we'll go out here to some point x final. How much work is going to be done by the spring in that case? Well, if we're going in that direction, there's our delta x, and the amount of work that will be done is the area that's in this little box here. In this case, it's going to be negative work because the force is actually going to be pulling back in this direction as soon as we displace ourselves in a positive direction. And how much is that? Well, the equation of this line is F equals minus kx. And so this thing right here will have a value of minus kx final. And the area of a triangle is 1/2 the base times the height. Well, the base is x final. The height of the triangle, height is negative in this case, so it's got a little different meaning, but it'll end up being, this will be the work that's done by that spring as you stretch it by this distance x final, it's going to be minus 1/2 k times x final. That's the height of the triangle times x final. Oh, well, that's just minus 1/2 k x final squared. So let's imagine that at some point you had some mass attached to the spring and it was going in this direction and it was brought to a stop by the spring. This is what the change in its kinetic energy would be while it's being stopped. Or maybe it had even more speed, but you could figure out, if you knew the speed here, you could figure out the speed here because you'd know how much work was done on it, and that would be the change in kinetic energy. So things like that are going to show up. Let's see, what else? Oh, well, maybe you didn't start at the origin. Okay, how much worse could the math get? Let's see, this is that problem I just did. I accidentally printed 2 of them. But let's suppose that we have, this is x initial. Here's our force as a function of x graph again. Here's our x thing. Whoops, that was supposed to be x initial. Here's our x final over here. And we'll have this spring doing the same thing again. So now we're going to have to figure out right here the area of this trapezoid. Okay, well, if you were doing this in calculus, you'd be doing this. The integral from x initial to x final of, let's see, it's just going to be kx dx minus kx dx. Or in calculus, that's what the scary looking hieroglyphics of calculus would show you. And for those of you who've taken second quarter calculus, you're going to look at this and think, ha, that's an easy integral. Okay, well, what this integral is going to be doing is calculating the area of this trapezoid. Okay, well, this is minus k x initial. Somewhere there's a formula for the area of a trapezoid, but I'll show you what it ends up being because we're going to derive it basically. This is minus kx final. Okay, well, we've got a rectangle and we have a triangle. For the rectangle, and this will be the work is going to equal just this area. So I'll add the rectangle and the triangle together. We'll have, they're both going to be negative because they're under the x-axis. That's something you'll learn in calculus. Anyway, I'll have x final minus x initial. That's the width of the rectangle. The height of it is minus kx initial. Actually, since I'm going to have these things on the dimensions, I don't have to have a minus sign out front. Plus, well, let's see, the area of this triangle is going to be 1/2 the base of it, which is x final minus x initial, times the height of it, which is, let's see, minus kx final minus kx initial. That's where the minus sign comes from. And I'm going to take that minus sign and stick it in front and just call this, whoops, kx final minus kx initial. When you get all the way done with this thing, you're going to find out, and if you play around with the algebra, you'll find out that it ends up being minus 1/2 kx final squared minus 1/2 kx initial squared, which actually ends up being the first term in there, ends up being the area of this entire thing. The second thing, this ends up being the area of this little triangle. So you're taking this entire area and subtracting off this little tiny area, and that gives you the area of this trapezoid here. So we didn't need calculus to do that. Okay. Anyway, that's something that's gonna show up on these things. And I think I printed off yeah, here's a spring problem. And we have a 250-gram block, that would be 0.250 kilograms, is dropped onto a vertical spring with a spring constant K equals 2.5 newtons per centimeter. The block becomes attached to the spring, and the spring compresses 12 centimeters before momentarily stopping. While the spring is being compressed, what work is done? A, by the block's weight, and B, by the spring. So here's the situation. We'll do a sketch of this. So we've got this spring here with a platform on top of it of some sort. And this starts off at its equilibrium thing. And we drop this block onto here that has a mass of 0.25 kilograms. And I can't say any more about significant figures than that because I don't know if the zero is significant or not, but it's that much. And anyway, it's falling downward, so heading down, and it lands on top of this thing and then compresses the spring by some amount, 12 centimeters before it stops. So we'll imagine that this mass has just reached this thing, 0.25 kilograms. And at that time, it has some downward velocity, which I'm just going to call V naught. Okay, because we're interested in the time period that starts when it just contacts this thing. Okay, well, it's going to have some initial kinetic energy. So KE initial is going to equal 1/2 m V naught squared. It compresses this thing by some amount, and the KE final is going to be 0 because it comes to rest after compressing that thing by 12 centimeters. Well, let's figure out how much work is done by the block's weight during that time and by the spring. And I'm going to convert this thing. I'm going to take that spring constant, K, and change it from newtons per centimeter to newtons per meter. Now, this is an exact conversion factor, and so I'll keep my 2 sig figs, but I'll end up with, for K, 2.5 times 10 squared newtons per meter. Okay, so there's my spring constant. That'll help. And I've already converted the mass, 12 centimeters. If you can't do this in your head, just multiply it by 12 centimeters by 1 meter over 100 centimeters. Centa means 100. So, or it means 100th, I think is what it means. Probably, yeah, 100th. So anyway, it'll end up being 0.12 meters. So that's going to be the compression of the spring, the maximum compression. And what else? I already converted the 250 grams into kilograms. If you're wondering about that, okay, 250 grams times, let's see, 1 kilogram. Kilo is metric for 10 to the third, so that'd be over 10 to the third grams. And when you move the decimal spot over 3 spots, you get 0.25 kilograms. So that's where all those conversions come from. And if you're confused about when do you move it 2 decimal places and when do you move it 1, just go through this process every time. And you should have memorized that 100 centimeters equals 1 meter. 1,000 grams equals 1 kilogram. 10 to the third. All right. Okay. What's the work done by the block's weight and by the spring? Well, how much work is done by the weight? We've got mg downward, and we have a displacement downward as well. The work done by the block's weight, W sub W, work done by the weight, is going to equal mg dot d, but they're both in the same direction, so it's just mgd, and the d is the 12 centimeters, 0.12 meters. So we'll take our, let's see, forgot what the mass was. Oh, there we go, 0.25 kilograms times 9.81 meters per second squared times the 0.12 meters mgd, and we'll get some number. Now the units are going to be kilogram meter squared per second squared, and we found out yesterday that a kilogram meter squared per second squared is a joule. By definition, that's an exact conversion. So and I have to do extra keystrokes because I always start punching numbers in before I check to see if it's on or not. And I get about 0.29 joules minus, or positive, excuse me, positive 0.29 joules. All right, what about the work done by the spring? Okay, we're starting from the equilibrium position. We're compressing the spring. And if I go back to my graph here, I didn't do any like this, but what we're doing in this case is we're starting from the equilibrium position and going in this direction. So in this case, delta x is going to be negative, and then we'll have the height of the spring up here. This will be kx final there, but x final is negative. We started off at 0. And so the work done by the spring in this case, work done W sub s, is going to be minus 1/2, it's area of a triangle in this case, k times x final squared. And because this part is going to be positive no matter what we do, we have to know that it'll be a negative work. But actually the work done by a spring is negative whether you're stretching it or compressing it. In both cases, the force is in the opposite direction from the displacement. So anyway, minus 1/2 times k, there it is, 2.5 times 10 squared newtons per meter times 0.12 meters, and that's squared. And this will be what slows that thing down. Gravity would tend to speed it up because it does positive work during this stretch. So 0.5 times and I get minus 1.8 Newton meters, which is the same as a joule. It's the same as a kilogram meter squared per second squared. So that's also equal to 1 Newton meter. So minus 1.8 Newton meters. Okay, what does C ask? Oh, what was the speed of the block just before it hit the spring? Well, the net work, which is going to be W sub S plus W sub W. And when I look at these things, I have to take into account their signs. That would equal the change in kinetic energy, which is the final kinetic energy, KE final, minus the initial kinetic energy, KE initial, and the initial was the 1/2 mv naught squared. Okay, well, that will equal, I've got minus 1.8. Oh, I said Newton meters. That's the same as joules. So I've got minus 1.8 joules plus 0.29 joules. And that'll equal the minus 1/2 mv naught squared. And I can't make the masses divide out this time because the work that was done by the spring had a K in there and not the mass of the thing. It's dependent on the strength of this force. So let's see. I must have some blank paper here I can swipe or go into. Anyway, well, what I'll have is minus 1/2 mv naught squared is going to be, when I add these two together, this is essentially 0.3, or I can only keep to that place. So it's minus 1.5 joules, or multiply both sides by 2, and I'll get mv naught squared by minus 2 actually will equal 3.0 joules, or v naught squared will equal 3.0 joules divided by the mass, which I keep forgetting, 0.25. And remember, a joule is a kilogram meter squared per second squared. So the kilograms go away, and I'll get, let's see, 4 times 3 is 12 meters squared per second squared. So just taking the square root of 12, which ends up not being so bad. And forgot to turn the calculator on again. I get about 3.5 meters per second. Now that's just the speed, doesn't tell me anything about the direction, but I know that it was falling downwards. So there we go with that one. Okay, let me go back to some of the earlier problems for today, if I can remember where they are. We're doing 12. Oh, this one. Nope, not that one. This one is one that I've had on tests before. And it's just kind of it's a conceptual question, but it's something to think about. So the block is pulled up an inclined plane by a cable, as shown in the figure below. There's friction on the plane, and the block moves at constant speed. Okay, so then it asks, as it moves up the plane, which forces acting on it do positive work, which do zero work, and which do negative work? So let's make a free body diagram for this thing. The low-hanging fruit is always mg. Okay. And we'll have this thing. There's friction. It's being dragged up the plane, so the friction is going to point down the plane, and this will be kinetic friction in this case, so there will be a force down in that direction. There's a normal force. It's on a plane, and the normal force is going to be like this, perpendicular to the surface of the plane, and it looks like that. And then we have the tension here that's in that direction. So as it goes up the plane, which forces acting on it do positive work? And then explain carefully. Well, I'll do the explaining out loud. I'm not going to write out sentences here, but the displacement is up the plane. So that's the direction of the displacement while we're dragging it up there. And any force that's in that upward direction will do positive work. And the only force that is the tension. Okay. That's it for positive work. Which do zero work. Okay, now remember, the work that's done by a force, in this case, we've got constant forces and we have a straight line displacement, but it will equal whatever that force happens to be dotted with the displacement. Now, something about that dot product, it's magnitude of F, magnitude of D, and the cosine of the angle between the force and the displacement. The cosine of 90 degrees is 0. So any force that's perpendicular to the displacement is not going to do any work. Well, the displacement's up the thing parallel to the plane. What's perpendicular to that? The normal force is perpendicular to the plane. So zero work is done by the normal force. And then negative work. Well, the friction definitely does negative work. It's pointing in the direction opposite the displacement. And if you take the cosine of minus 180 degrees, you get -1. By the way, it's a good idea to just be able to quickly remember things like that. And we do it often enough. If we graph the sine of theta, its curve looks like a sine wave, oddly enough. And it starts off at 0 radians. It's got a value of 0 at pi radians or 180 degrees. It's got a value of 0, and in between it reaches a maximum value of 1 at 90 degrees or pi over 2 radians. And so you should be able to remember something like that. And then for the cosine, it does something like this. At 0, it's got a value of 1. At 90 degrees, it has dropped down to 0. So here's 90 degrees. And at 180 degrees, it's down there at -1. So keep those things in mind and just be able to quickly sketch these things out. They pop up often enough that it's nice to use them. So this would be 270 degrees and this would be 360 degrees. It's back up to 1. So just remember those things. So what's going to do negative work? Anything that's pointing opposite this or that has a component pointing opposite that. And if you look at mg, it's got a component that is opposite the displacement. So negative work, friction for sure, because it points opposite the displacement, and weight. That also does negative work because it has a component opposite the displacement. One of its components is perpendicular to the displacement, but that component that's opposite that means it'll do negative work. Okay, then it says, which force acting on the block does the most work in magnitude as the block moves up the plane, and explain your reasoning. Well, there's a key thing up here. The block moves at constant speed. So as it goes up the plane, there is no net work being done. There's no change in kinetic energy. So no change in KE means no net work. That means the work of tension plus the work of friction plus the work of gravity equals 0. Well, these two things are negative. Okay, so the work of the tension ends up being the absolute value of the work of the friction plus the work of gravity. So the tension in this case has to do the most work because it's got two forces that it has to overcome. The tension does. Okay, there's one. I don't remember where I was actually going to start on this list. Yeah, here's one that if you could ignore air resistance, from what height would an automobile weighing 12,000 newtons have to fall to gain the kinetic energy equal to what it would have when going 89 miles per hour or 89 kilometers per hour? That's not a bad problem. You might try that one on your own. This one, though, is tosses in a new idea. 1,430 kilogram block is pulled up a 14-degree incline at a constant speed of 1.34 meters per second by an electric winch. The coefficient of kinetic friction between the block and the incline is 0.40. This is just like the situation we just looked at, except we're given numbers here, but it asks, what is the power output of the winch while moving the block? Now, power is something that we haven't talked about yet, but it's got a new definition. Power, it's got a couple definitions. For us here, we can talk about power as being the rate at which work is done. Okay. Now, whenever we're talking about a rate, we're talking about something being done or something happening, and we divide it by the time during which that stuff happens. So in this case, power is equal to the work divided by the time that it takes to be done. In general, we may talk about power in situations where work isn't necessarily being done. And a more general definition for power is that it equals the rate at which energy changes from one form to another. Okay, now work over time. Our units of work are going to be joules. Our units of time is going to be seconds. And here we go again. We've got a new unit being introduced. A joule per second is equal to a watt. Actually, I don't remember what which one of them, either watt or joule, had a first name of James, but I don't remember which one was which. But anyway, it's a watt, and the abbreviation for it is a capital W, and it's unfortunate because we're using that for our symbol for work. But that'll be the unit of power at any rate. And so I'll try to write things out in words if I'm going to have a watt being a final unit and we're talking about work. I may just, I don't know, use a formula to calculate the work instead. You may have, I don't know, dealt with watts before. I remember one time at our home, I had 3 daughters who were all teenagers at the same time, and often the hair dryer in the bathroom would be getting a lot of use in the morning. And the hair dryer had a power use of something on the order of 1,500 watts. And so that might be the power consumed by a hair dryer, or a toaster might be comparable to that as well. So there's something. Let's see, a bright light bulb, the old incandescent light bulbs, the brightest ones, about the brightest ones you might typically buy, were a 100-watt light bulb. Now, that was the power consumed by the bulb. Turns out most of that energy did not go into light, it went into heat. And those old incandescent light bulbs would get really hot when they were operating, and you did not want to unscrew one of those right after it had been turned off, because you'd burn your hands on it. So most of that energy went into heat. Nowadays, if you buy a light bulb, it may have a rating on it of the watt or the power equivalency to compare it with the old incandescent light bulbs, but it may only consume 9 watts or something like that with the LED bulbs. They're much more efficient and don't get nearly as hot. By comparison with that, something that puts out a lot more power is a thing that does a power output of about this 3.86 times 10 to the 26th watts. That's the power output of the sun, and it puts out a lot more. Now, in the case of a hair dryer or a light bulb, it's taking electrical energy and converting it into heat in the case of a hair dryer or a toaster. In the case of a 100-watt incandescent light bulb, it's taking electrical energy and converting most of it into heat, but some of it into light. In the case of the sun, it's actually doing a trick like this. It's losing mass every second while it's doing that, and it's losing it at a rate that it produces that much power. So it's actually converting mass into electromagnetic radiation energy. This power for the sun is measured across all parts of the electromagnetic spectrum, and that's what it happens to be doing there. Well, that was a long aside, and now I don't have time left to solve this problem. So I think I may do this one in a supplemental video, and I may do a couple others in there for power stuff. So something else that I think I want to do is looking at the quizzes that people were taking. I saw some common stumbling blocks on them. This is the quiz on the two-body problems that you did with the inclined plane. And I think I'm going to record a video where I do those as well, because we could overcome some hurdles there. I'll be posting these problems up there and also this video. And something else I want to do, really do a very scientific survey of when would be the best time for meeting. And it seems to work out for 11. It seems like there were some hours that nobody could do. So, but also something that I wanted to ask you about is, would anyone be interested in a perhaps a Friday office hour or problem solving session? And what might be a good time for that? I wouldn't want to do it late in the afternoon on Fridays, but possibly sometime in the morning or early afternoon. Is there a time? And I know a lot of you work Fridays, so it might not work out at all for you, but I'd just like to ask you about that if you wanted to ask questions on that week's homework or something like that. So watch for a survey that I'll post about that. And what it would be is just a Word document, and it'll have squares that you could type preferred times into or something like that, or you could put X's in the boxes, something like that, and then just save it as a PDF and submit it. So that's what it'll be like. So anyway, are there any questions while I'm still on here about stuff that I did today? And if there are, you could either type them into the meeting chat or make your microphone live, and I can't remember how you do that, and ask them out loud or whatever. And if not, we could knock off for now, and you can start working on stuff for the weekend. I posted the assignment for the new homework and the lab that we did this week too already. So those will be due next week. I think the lab is due Tuesday night at 11:59 p.m. Okay, I don't see anything popping up and I don't hear anything, so I may just stop here and let's see, stop